Hello, everybody. Uh, Welcome to Surrey Geometric Analysis Festival. My name is Flavio Almeida Lemos. I'm from Brazil at the Ouro Preto Federal University, Ouro Preto City, right? This work is I made together with my partner, Ezequiel Barbosa, right? We divide this presentation in two videos. The first one is let's go now. Okay. A usual strategy in conformal geometry consists in choosing a metric in the conformal class of a fixed metric G, such that the geometry becomes simple in the sum aspect. For instance, Yamabe proposed the following problem. Given a closed Riemannian manifold of dimension n, find a Riemannian metric conformal to G with constant scalar curvature. Right? It's proposed by Yamabe. Right? We have the following equation. This equation. It's the metric G tilde is that way, has constant scalar curvature lambda if and only if the function satisfies the following partial differential equation, this equation. Yamabe noted this equation is Euler-Lagrange equation for the functional. All right. We have to introduce to the Yamabe invariant. Yamabe invariant is the number defined by the way. Right, or we consider the number m as a ring over this functional, where G is conformal to G tilde is conformal to G. Satisfy G tilde satisfies this quality. All right. This constant is invariant in the conformal class. Is a code Yamabe invariant. All right. We introduce first the geometric. First, the Riemannian context. Okay, when any is equal to, the my problem is equivalent to the uniformization theorem in complex analysis. When any greater 3, the my problem was completely solved by Trondken, Aubin, and Chen. All right. We introduce first the Yamabe problem on Riemannian geometry context. Here, all manifold is compact. All right. Let's go to introduce the CR context of the Yamabe problem. Okay, the Yamabe problem on CR manifolds, right? Called the Yamabe problem on CR manifolds, given compact pseudo-Hamiltonian manifolds and theta, strictly pseudo-convex. All right. The problem here is found a structure, pseudo-Hamiltonian structure, theta tilde, the same orientation of theta, such that the pseudo-Hamiltonian scalar curvature is constant. We have the same perspective on geometry here, right? We need to find the other pseudo-Hamiltonian structure conformal at theta tilde, conformal to theta, such that pseudo-Hermitian scalar curvature is constant. Okay, it's the same problem, but in the other perspective, other geometry. Okay, other context. Okay, the same way, the pseudo-Hermitian structure theta 2 satisfies this, has pseudo-Hermitian scalar curvature lambda if and only if satisfy the equation. This equation. See, this is a sub-Laplacian. Later, I introduce the sub-Laplacian. Okay, it's a scalar curvature in the theta. Okay, all right. This is a Euler-Lagrange equation of this functional. P is different here. P is equal to minus 2 divided n. Okay, 2 plus 2 divided n is different of the Riemann contest. This is value here. All right. We define the same way the Yamabe invariant on CR context. Okay, it's called CR Yamabe invariant because it's invariant over CR maps. All right. Just some proof, solve the problem. Prove this theorem. Says a sphere. Here there's complex space. It's a unit sphere with the pseudo-Hermitian standard pseudo-Hermitian structure. CM theta is a compact pseudo-Hermitian manifold of dimension. It's a dimension of pseudo-Hermitian manifold, compact pseudo-Hermitian manifold, with the Yamabe invariant. Then M depends only on their CR structure on M. Okay, M is less or equal the invariant of the Yamabe variant. The Yamabe variant is less than Yamabe variant of the sphere. This is a sphere, CX sphere, in complex space. Okay, if we have strictly inequality, then M admits a conformal pseudo-Hermitian structure with constant pseudo-Hermitian scalar curvature. Okay, I will have this mean we have the function U that satisfies this equation. Okay. All right. It's necessary to prove this. There's only proof. Proved. Let M be a compact, strictly pseudo-convex manifold of dimension satisfies this inequality. Is not locally CR equivalent to the sphere. All right. Then we have an equality such that we have pseudo-Hermitian structure with constant pseudo-Hermitian scalar curvature. All right. Is it true? See, it is not true first, this theorem. It is supposed. This is a result. All right. We have the proofs is and the CR equivalent, not manifold, is not locally CR equivalent to the sphere. Okay. The gamma complete the Yamabe problem CR geometry. Let M theta be compact pseudo-Hermitian manifold of dimension 2n plus 1, CR equivalent to the sphere. It's meant for the CR equivalent to the sphere. Then M admits pseudo-Hermitian structure with constant pseudo-Hermitian scalar curvature. All right. Right. E theorem Yamabe complete in the case of dimension 3 is not equivalent to a sphere. Right. So we have the Yamabe problem CR context proved completely proved. All right. Right. First, we introduce here. Omar introduce the second Yamabe invariant. Let's see. Let's here be a second is a Yamabe operator. Okay, we have the Riemann manifold. Consider the Yamabe operator. Since the Yamabe operator has discrete spectrum, it's an eigenvalue of this Yamabe operator. All right. We will define the second Yamabe variant using the second eigenvalue of this operator. Right. We define two the same way we can define the Yamabe variant using the first eigenvalue if over the conformal class of the fixed metric G. This is a volume, the volume term. All right. Then the Homan introduced the second Yamabe variant using this like a motivation. All right. He defined the second Yamabe variant this way over the conformal class. This is taking over the conformal class, right? Abba, Aman, and Humbert, after introduced this second Yamabe variant, proved the following theorem. Let Mg be a compact connect Riemann manifold with dimension n larger than 3, with the first Yamabe variant O, the Yamabe variant is positive. Then we have the inequality, right? The second Yamabe invariant is less than second Yamabe variant on CR sphere. Furthermore, the equality occurs if and on if Mg is conformally diffeomorphic to the sphere. All right. We with my partner, we proved the same theorem in the CR context. We define the second Yamabe variant in the CR context. All right, improve the same. We prove the same result on the CR contest. All right. The LCIAD prove the following theorem. Let Mg be a compact Riemann manifold with dimension n larger than 3. Here, the Yamabe variant is strictly negative. Okay, it's different here. Here, the Yamabe variant is strictly negative. All right. We denote lambda 2, the second eigenvalue of the Yamabe operator. Then, if Mg is not locally conformally flat and dimension satisfies this equation, this inequality, there exists a signaling change function, W, solution of the equation. Here, epsilon, where epsilon is +1 if lambda 2 is strictly positive, epsilon minus 1 if lambda 2 is strictly negative, epsilon is 0 if lambda 2 is 0. Moreover, we have this regularity for O alpha less n minus 2, where less is this number, n as a dimension. In this lecture, we try to prove the same theorem that also had in geometry context. Some restriction. We have some problem with geometry, with relation with the Riemann geometry, right? We need this some condition here. All right. We introduce the second CR Yamabe invariant the same way. Okay. Where the lambda 2 is the second eigenvalue of CR Yamabe operator, where we replace theta with theta tilde. All right. We have the same result among result. It's here. We have in CR context. We prove the following theorem that M theta bear compact connect strictly pseudo-convex pseudo-dimensional manifold with dimension satisfies inequality. With the Yamabe variant is positive. Then we have this equality like here, Amann and Humbert. Okay. Furthermore, equality occurred if this manifold is locally CR equivalent to the sphere, CR sphere. Okay. We have the same result. Change here, conformally diffeomorphic to a sphere. It's a change by locally CR equivalent to the sphere. All right. We stood the main idea here is to prove two equivalent LCI theorem on CR contest. We have proved this theorem this lecture. Suppose that M theta is compact, strictly pseudo-convex, 2n plus 1 dimensional CR manifold, not CR equivalent to a sphere. If n dimension, and n is not dimension, n is number here, dimension 2n plus 1. Okay, if n is strictly greater than 4, and the Yamabe variant is negative, then we have strictly inequality. Okay? All right, the first the Yamabe variant, CR Yamabe variant on CR sphere. Okay. Our theorem, it's main theorem here. Right, so it's the theorem of the lecture, of this lecture. It's the main theorem of the lecture, where this have let him be a compact strictly pseudo-convex 2n plus 1 dimension, CR, manifold not CR equivalent to a sphere, with n is greater than 4. If the Yamabe CR Yamabe variant is negative, suppose that there is a constant. We need to suppose also that there is a constant B0 such that satisfies this equation inequality. With U, this space, it's a Fallen space, Fallenstein space. It's like Sobolev space in CR geometry, CR context. Okay, then there exists a signal change function, W, solution of this equation, where epsilon is +1 if is lambda2 is positive, epsilon is equal to 0 if lambda2 is 0. We have the W satisfies this regularity, or O alpha satisfies this inequality. All right. Following a similar idea as that of LSAT, we studied a result similar of that measured above on the CR context. All right. We have this following organization. Okay, in this first video, we introduce the problem. We introduce CR manifolds. Okay, and then we finish in the second video. All right. So what is CR manifold? A CR manifold is a differentiable manifold endowed with complex subbundle. It's a T10 of the complex side tangent bundle. All right. Such that satisfying. It's satisfying. E in this is the integrability property. The bundle is the CR structure of M. With dimension, it's a dimension. We call M CR dimension of M. We set this way, T01, if dimension is 2n plus 1, and M is equal to n. It's called of the type hypersurface. All right. To define what is CR manifold, we need there exists a subbundle when complexify the tangent bundle. Okay, satisfies these properties. All right. The third structure determines the distribution of her real rank to n. It's a distribution. We take the real part, this, equal the Levy distribution. We have a Levy distribution over all manifolds. Okay, it's a subbundle, subtangent bundle. We have the complex structure 2, given by the way, Z is here. Z is here, all right? The CR map, a map this that preserve the CR structure. The CR structure here go to CR structure here, like this way, all right? Okay, we define to the Levy form, by the way, for y choose xy t10. This Levy form is positively defined and strict pseudo-convex. If Levy form is positively defined and strictly pseudo-convex, all right? We have a frame to the section defined this way, in an linearly dependent sections on HM, we define this way. Okay. Our pseudo-Hamiltonian structure determines a characteristic vector field T, where it's important this is vector field defined by it's 1 here, it's 0 outside. All right. These are stereo derivative of the form. Okay. would extend the Levy form on complexified subbutton. We have the Levy form this way. All right. We define using the pseudo-Hamiltonian form. We define the metric over the space. All right. This way, with extension determines a Riemann metric on called Webster metric. See the projection associated with the direct sum. Then the Webster metric may be written as this way, right? We introduce two pseudo-Hamiltonian connections. Okay? Our pseudo-Hamiltonian structure induces a natural linear connection on M with the notes this way. This connection is different of Levi-Civita connection. We have torsion here, right? We have a torsion term here, all right? This torsion is pure, but if I see this inequality, we have this a relation between the torsion and the Levy form. Okay, so it's satisfied here. The math Tanaka proved that there exists a unique linear connection on M satisfy the following axioms. The Lie distribution is parallel with respect to this connection. Perhaps this satisfies these properties. The complex structure is parallel, the metric is parallel. We have the torsion term is pure, satisfies these properties. Okay, I define that have a definition of pseudo-Hamiltonian curvature, right? The same way you have in the Riemann contests. We have the Webster curvature tensor. You have the Hitch tensor, the same way. We have the Riemann contest. Okay. The pseudo-Hamiltonian scalar curvature definitely with respect to the forms curved as the contraction of pseudo-Hamiltonian Hitch tensor defined above. We have the pseudo-Hamiltonian scalar curvature. Okay. Like we have now the similar normal coordinates in Riemannian contest. We have pseudo-Hamiltonian normal coordinates on CR contest. Okay. The same way you have the Euclidean space on standard geometry in the Riemannian contest. We have the Heisenberg group here on the CR contest. The Heisenberg group is defined by the following way. We have a product, and this is the Heisenberg group is a manifold with the product where Z is a linear is complex number. The line here is a real number. All right. We consider the Heisenberg group to be a pseudo-Hamiltonian manifold with Lamarck tangent bundle. Okay, with standard contact form. Okay, we have the map, the following map given by the way. Okay, SZ S2T for and ZT in the Heisenberg group. It's a code dilation by the factor S. Consider the vector field this way. I will have the Heisenberg norm. With the Heisenberg norm, we have the dilation satisfies these properties. Right? Then we have the pseudo-normal coordinates. Okay, the orbit of the dilation lead parabola through zero for fixed WC. It's a parabola. We have now the first idea here. Study these parabolas on Heisenberg groups and try to put this and CR manifold general. Right? We have these curves. It's called the parabolas. Its image is the parabola contain the orbitals WC, minus WC, tangential vector, and zero. Its origin, its W0 is for S referent of the zero. We have this equation. Okay. Right. Use the dilation above to define these curves. All right. Use the fact that the pseudo-Hamiltonian connection again satisfies this equation. That satisfies this equation. This curve satisfies this equation. The main idea here introduce the similar curve we have the Riemann contest. This curve called the Riemann contest geodesics. In the CR contest, this curve is called the parabolas. Parabolas curve. All right. Let me on the manifold. Let satisfy this equation on this initial condition. Okay. We have the parabolic exponential map. We define the parabolic exponential map. Okay. Then we have equation we have curve on the Riemann or the CR manifold satisfies this equation. Different. It's not zero. We have torsion here. We have this a characteristic direction. All right. It's true. The solution of this solution to this equation on CR geometry general. Okay. We define the parabolic exponential. It's similar, the parabolic, the exponential on Riemann manifold. Okay. We get this result. Okay. All right. Their idea here is created pseudo-Hamiltonian normal coordinates, like normal coordinates. We have a similar normal coordinate and Riemann contest on CR contest, but the CR contest called pseudo-Hamiltonian normal coordinate in the geodesic curve in the Riemann manifold is treated here like geodesic parabolic curves. This is the geodesic parabolic curves, right? We have a relation locally on the geometry, CR geometry. Locally, we can treat the CR geometry like a Heisenberg group. All right. Let me introduce the sublaplacian. Okay, we have the volume element definite on pseudo-Hamiltonian manifold like this. The volume, the manifold is compact. All right. We define sublaplacian. It's a sublaplacian. What is the sublaplacian? We define this way. Né? We define the gradient, subgradient is a projection over AGM. All right. It taken the after projection. We take the trace nowhere. Divergent. All right. You get the sublaplacian. Okay. Similar to Sobolev space in this Riemannian context, we have the Fallen space here. Fallenstein space. We define it this way. All right, observer here, we take out the direct derivative and the direct and the criteria direction. We take out the derivative on the criteria direction. Define the Fallen space this way. Define the norm first. LP norm 2 locally, okay? And we have a definition of Fallenstein space. It's the complement of C0 locally on the norm above. All right. The manifold is compact. We can define over O manifold, right? We have the same embedding theorem. All right. We have the similar Kondrakov theorem. Okay. We consider the following equations. The idea is minimizing this following equation. Okay. I will prove we can write the. Let me remind it's a Cartesian eigenvalue of the CR Yamabe operator. All right. Okay, can define this way. Right. It's the first video to introduce geometry. Okay. In the next video, we prove the lecture theorem, main theorem. All right.